Lesson 10.1 Part 2, Evaluating Limits, Indeterminate Form. All right, let's take a quick moment here, a little bit of review of what you learned in the last lesson. Go ahead and pause the video here and evaluate each of these limits. Play when you're ready. So you learned in the previous lesson that the simplest way to evaluate a limit is just using direct substitution. Take the x value, plug it in, and see what you get. So for the first one, limit as x approaches 1 of x squared minus 4 over x plus 2. We're going to start just by plugging in 1 for x. When I do that, I stop writing the limit and I replace the x with 1. 1 squared minus 4 on the top would be negative 3, over 1 plus 2 on the bottom would be positive 3, which when I divide, I get negative 1. So the limit exists at negative 1. On the second question, we'll do the same thing, plugging in 2. So 2 squared minus 4 on the top is going to give me 0 on the top, 4 on the bottom, and 0 divided by 4 is 0. Remember, 0 on top equals 0. 0 on bottom is undefined. 0 on top is 0. And the third one, this time we're going to plug in negative 2. So negative 2 squared minus 4 over negative 2 plus 2. But this time something interesting happens. We get negative 2 squared or positive 4 minus 4 on the top, which is 0. We also have 0 on the bottom. So this is where we need to pause and think about, what does that mean? Now, I just said a moment ago, 0 on the top means the answer is 0. So here I have 0 on the top. Does that mean my answer is 0? But I also reminded you that if 0 is on the bottom, then it's undefined. Well, here's 0 on the bottom, so is the answer undefined? Or, throw a curveball at you, I have the same number top and bottom. When I have the same number top and bottom, shouldn't the answer be 1? So, 0 over 0, is the answer 0? Is the answer undefined? Or is the answer 1? Go ahead and think to yourself, make a guess to yourself, what do you think the answer is going to be? And that's right. None of those answers are correct. This is what's known as indeterminate form. 0 over 0 is not determinable. I cannot determine an answer when I have the statement 0 over 0. To say something is indeterminate is to say that there are competing rules that all have equal validity, and yet no one rule can be said to be right over another rule. For instance, I have the rule that says 0 on top says my answer is 0. I have the rule about 0 on the bottom means my answer is undefined. I have the rule that says anything divided by itself equals 1. I have 3 different rules that can be applied to this situation, and all 3 rules would produce a different answer. Therefore, I have no idea which one is right. And as I said a moment ago, actually none of those rules are right. So anytime you get 0 over 0, we're not going to stop right here. We need to keep going because 0 over 0 is not an answer. You have to use some other technique in order to evaluate it. And that's what today's lesson is going to be all about. The previous lesson was for well-behaved functions, for continuous functions that work by direct substitution. Now let's look at these not so well-behaved functions where direct substitution fails. What happens when I get 0 over 0? As I touched on in the previous lesson, you can evaluate a limit by looking at a graph. Well, I have a graphing calculator. If you don't have yours handy, go ahead and pause the video and grab it. Hopefully you have your graphing calculator ready now. So let's take a moment and take the function that we're confused about, x squared minus 4 over x plus 2, and let's graph it in our calculator. So notice I've got on the y equals screen x squared minus 4 over x plus 2. And just so to make sure that we are all seeing the same thing, here is the window that I'm using. Negative 6 to 6 in the x direction, and then negative 6 to 2 in the y direction, and I accidentally covered this up. The y scale should be left at 1. So when I graph it, this is the graph that I get. Now, depending on what calculator you're using, you may get something that looks a little bit different. Again, here I'm using the newest update to the TI-84 series, but if you're using one of the older TI-84s or the TI-83, you may see something that looks like this. Now, here's what I see, here's what you see. Here's what I see, here's what you see. Now, if you have the newest calculator, then you notice something really interesting happening right here. Oh, yes, you are absolutely correct. There is a hole in the graph. At x equals negative 2, which is where I'm trying to evaluate my limit, this function has a hole in the graph. Now, if you're using one of the older calculators, you're not going to be able to immediately see that from the graph, but it is there, and we can test whether you're using the old operating system or the new operating system. You can test the fact that there's a hole by simply tracing an input value. So if you hit trace -2, enter, it should spit out nothing for your y value, which indicates that the graph has a discontinuity at x equals -2. Now remember, discontinuities come in really two flavors, vertical asymptotes and holes, and by inspection this is clearly not a vertical asymptote. So even if I'm looking at this version of the graph, this is clearly not a vertical asymptote, so that means there must be a hole at x equals -2. Now, knowing that there is a hole allows me to make a conclusion because the limit as we approach a hole will exist. We saw that in the previous lesson. And if there's a hole in the graph, the fact that the graph doesn't exist at that point is not relevant. The limit can still exist. So if I look at the graph and I try to predict, okay, to what y value is the graph headed? Well, to me, it looks like it's headed to a y value of -4. All right, but keep in mind, I'm using my human eyes to justify that conclusion. It would be just as valid for me to conclude that the graph is headed to -4.1 or -3.9 or -3.9995 or -4.00128. A graph is a good argument, but it is not proof that the answer is indeed 4. It looks like the answer is -4. If this is all the evidence I have, then I'd be willing to conclude that the limit is -4, but I wouldn't bet anyone's life on just looking at a graph. Another option that we can do is called the numerical approach. Numerical approach to evaluating limits is essentially creating a table of values where I have x's on one side and y's on the other. Good news is our calculator will do that for us. Just like our calculator will graph for us, you can create a table of values using your calculator. So again, if you're using either the TID3 or the TID4 series of calculators, if you hit second table set, and the table set button is actually the same as the window button. So if you hit second window or second table set, you should see this menu pop up. And you have to tell the calculator where you want to start your table, and the little triangle there, again, that's the Greek letter delta, so the change in the table or the step size. So I'm going to tell my calculator to start counting at -2.5, which is a little bit to the left of -2, and I'm going to count by 0.1. Anytime you're evaluating a limit, you don't want to take large step sizes. A step size of 1 is huge when we're talking about limits. 0.1 is still actually pretty big, but it's reasonable enough it's small enough to be within reason. The reason I'm starting my table at -2.5 is because I happen to know that my calculator will display 11 lines on the table. So if I started at -2.5, it'll go from -2.5 to +2.5 and show me 11 lines with -2 in the middle. If you're using the older TI-83 or TI-84, that one's only going to display 7 lines, so you may want to start at -2.3. But no matter where you start, once you open up the table, which is the graph button, so instead of hitting graph, hit second graph and it'll display the table. Notice that it starts on the x side, it starts at -2.5, which matches right here, and then the step size is 0.1. Again, if you're using the older calculator, start it at -2.3, or you can just use the up and down arrows on your calculator at this point, and it'll slide that table up and down as many times as you hit the up and down arrow. Now, let's look at what's happening at -2. Notice we're getting an error, which makes sense because if I plug in -2, I don't get an answer. I get 0 over 0, and just like I have no idea what the answer is, the calculator has no idea what the answer is either, so it's just going to display error. But if I look on either side of -2, so here's the left side of -2, here's the right side of -2, as I get closer and closer to -2, look at what's happening with those numbers. -4.5, -4.4, -4.3, -4.2, -4.1, blank. -3.5, -3.6, -3.7, -3.8, -3.9, blank. So then the question is, what number would fill in that blank? Well, once again, still looks like -4 would fit perfectly in there. So remember, a limit is about where you're headed, not where you actually end up. So based on that table and based on the graph, both of these are really good arguments to say that the limit must be -4. But again, just like with a graph, a table, it's a really good visual argument, but it's not perfection. It is not impossible that I could be wrong. I think it's unreasonable to think that I'd be wrong to say that the answer is -4. It's perfectly reasonable to conclude -4, but math is not about perfectly reasonable. This is not a court of law where you just have to make a good argument. With math, the only alternative to a right answer is the universe no longer exists. All right, that is a much higher threshold of being right than just, well, I think it's a really good argument. The only way we're going to make a perfect argument is with an algebraic approach. So when you're evaluating a limit and you get 0 over 0, you always want to start with that algebraic approach, which is what I'm about to show you. If the algebraic approach doesn't work, then that's when we fall back to graphs and tables, because that's the best we can do. But the algebraic approach is always going to be the best option. Now, something I already know is when I evaluated the limit, I got 0 over 0. And something I already know, based on my prior experience of working with rational functions, is that the only way I'm going to get 0 on the bottom is if I have a discontinuity. Now, there are two main types of discontinuities, holes and vertical asymptotes, and that at a hole, the limit exists, but at a vertical asymptote, the limit does not exist. And if the limit didn't exist, I would have gotten that answer from the get-go. If the limit didn't exist, I would have gotten a number divided by 0, which is undefined, which means the limit doesn't exist. The fact that I did not get a number divided by 0 means I must have a hole. Anytime you get 0 over 0, the only conclusion you can make is that the limit exists somewhere. There's a hole in the graph, but I have no idea where that hole is. You can't conclude what the actual answer is, but you can conclude that there is an answer and that you have to keep hunting for it. So now that I know that there's a hole, I know there's a removable discontinuity, because that's what a hole is, which means I should be able to algebraically remove the discontinuity and then be able to evaluate the limit, because once I've removed the discontinuity, I will no longer have 0 on the bottom and I'll be able to get an answer. So let's do that. We remove the discontinuity by factoring the numerator, in this case x plus 2, x minus 2. Notice the x plus 2 cancels out, which removes my discontinuity, because of course the discontinuity occurred because I plugged in -2, so it must have been x plus 2 that was causing the problem. Now let's reevaluate the limit. The limit as x approaches -2 of x minus 2. Plugging in -2, I get -4. And now we have our answer. We had a good argument with the graph and the table that the answer was -4, but now I have beyond any possible doubt, not any reasonable doubt, but any possible doubt, that the answer is indeed -4. So going back to that calculator just for a quick second, just to visually remind myself of what it looked like. So what I now know is that at x equals -2, there is a hole at y equals -4. So I have a hole in the graph at the coordinate -2, 4. Or I could say that there is a removable discontinuity at x equals -2. Or in the context of this question, I could say that the limit exists at -4. So before I give you a handful of problems to try on your own, let's summarize everything that we know about limits thus far. First and foremost, note for every single limit question in the universe, the first thing you should try is direct substitution, because the best thing that can happen is you plug in your x value and you get a number. If you get a number, you're done. The limit exists at that number. Alternatively, you could try direct substitution and get a number divided by 0. This is just as good as getting a number. If you apply direct substitution, you get a number, then the limit exists at that number. If you apply direct substitution and you get a number divided by 0, that means that your limit does not exist, because a number divided by 0 is undefined. You could also say that there is a vertical asymptote in that case. In a vertical asymptote, the limit does not exist. Or option 3 is you get an indeterminate form. Now, we just looked at an indeterminate form 0 over 0. There are actually a bunch of different indeterminate forms, and if you take a calculus class, you'll learn about all the different types of indeterminate form. The two that you typically deal with in a pre-calculus class are 0 over 0 and infinity over infinity. Now, we're going to talk more about the infinity over infinity indeterminate form when we get to lesson 3. But for now, we're just going to stick to the 0 over 0 situation. And if you get 0 over 0, you know there's a hole. And if there's a hole, we're going to take our algebraic approach to remove the discontinuity in order to get our answer. Now, if the algebraic approach is a dead end, which it's possible, not every algebraic problem can be solved using the techniques that we are familiar with. If we're unable to algebraically manipulate the function to remove the discontinuity, then we can fall back to looking at a graph or a table and answer the question that way. Always start with direct substitution. You'll either get an answer or you won't. If you get an indeterminate form, then keep moving forward. And one more time, if you don't have this in your notes 14 times already this year, let's go ahead and put it in there a 15th time. 0 over 0 is indeterminate. 0 over 0, I have no idea what the answer is, but I do know that the limit exists. Keep working to figure out where it is. 0 on the top means the answer is 0. The limit exists, you're done. 0 on the bottom is undefined. The limit does not exist, you're also done. The only time that you're not done is when you have 0 over 0. If you get 0 over 0, keep working. If you get 0 over a number or a number over 0, you're done. 0 on top, the answer is 0. 0 on the bottom, it's undefined. Also 0 on the bottom, that's a vertical asymptote. 0 over 0, that's a hole. All right, here are 4 more problems. Go ahead and pause here, hit play when you're ready. All right, looking at the first one, we should always attempt direct substitution first. Don't jump into advanced techniques as your first step. Always start by simply plugging in the number and seeing what happens. If I plug in 0 for x, I get 0 over 0, which of course is my indeterminate form, which means I need to keep going. I'm gonna proceed by factoring out the numerator. X squared plus 2x is x times x plus 2. Now keep in mind, a big part of what you need to be focusing on as you are going through this lesson is your notation. If you did not write limit as x approaches 0 of x parentheses x plus 2 over x, then you will not get full credit on this problem. Your notation will be graded. Make sure that you're using proper notation. I have not applied the limit in this version of the problem. I have not applied the limit in this version of the problem, so that means the limit should still be there. Versus up here, 0 over 0, I did apply the limit, so I didn't write limit as x approaches 0 of 0 over 0. That wouldn't make any sense. Once I plug in 0, stop writing the limit, so I did not write the limit in front of the 0 over 0, but I did write a limit in front of the x parentheses x plus 2 over x because I did not replace x with 0. Keep going, I can cross out the x's, I'm left with x plus 2. Notice, once again, it says limit as x approaches 0 of x plus 2. I just dropped down that limit from level to level to level. Now, because I've removed the discontinuity, I can go ahead and reapply the limit, and you can either write your answer below, or what I like to do, because I'm plugging in the limit, I'm going to start writing horizontally. Because I'm going to take 0 and plug it in, I don't have to write the limit anymore. I'm just going to write 0 plus 2, or 2. The fact that I got an answer means that my limit exists. My limit exists at 2. So I can say that the limit as x approaches 0 of x squared plus 2x over x is 2. Or I could say I have a removable discontinuity at x equals 0, or I could say that I have a hole at the coordinate 0, 2. Here's another one. If you didn't already, pause here, play when you're ready. All right, I'm going to start by plugging it in. Now this one, I may need to do a little scratch work if necessary. The negative 2 squared, that's going to be positive 4, minus negative 2, minus 6, and then of course I'm definitely going to get 0 on the bottom. 4 plus 2 is 6, 6 minus 6, all right, 0 over 0, which is indeterminate. So now let's switch to algebra mode. Factoring the top, I get x minus 3, x plus 2. X plus 2 cancels out. I get x minus 3. I also want to point out here that when you go to factor that numerator, this should be one of the easiest factoring problems that you have all year because you already know what one of the factors has to be. If x plus 2 is what you have on the bottom, then that means I must have an x plus 2 on the top. The top has to factor into x plus 2 times something in order to get 0 on the top, because the only way I'm getting 0 when I plug in negative 2 is by plugging it into the factor x plus 2. So I know one of the factors is x plus 2. It's just a matter of figuring out what the other factor is, in this case x minus 3. So evaluating limit as x approaches negative 2 of x minus 3, means plugging in -2 for x, -2 minus 3 is -5. Once I plugged in the limit, I stop writing the limit, so I don't write limit as x approaches -2 of -5, I just write -5. Final answer. Here's the third one. Again, if you haven't already, pause here, play when you're ready. All right, so plugging in 3, again, a little scratch work might be necessary. On the top, that's going to be 9 minus 9 or 0. On the bottom, 3 squared is 9. So that makes that 18 minus 15 minus 3, which is going to be 0. So 0 over 0, once again, indeterminate form, factor everything out. Cancel the x minus 3. I'm left with x plus 3 over 2x plus 1. When I evaluate the limit, I should get 6 over 7. Final answer. And last one. Pause here, play when you're ready. All right. And I always like to throw in this one because, again, always try direct substitution first. Just because you see something that looks like another problem doesn't mean that you're going to follow the same technique as that other problem. All the 3 previous problems were indeterminate, which meant go straight to factoring. But on this one, if you go straight to factoring, first, you're going to get the wrong answer. And second, what do you mean go straight to factoring? The top is not factorable. X squared plus 1 cannot factor. If you factored the top into x plus 1, x minus 1, you messed up because x plus 1, x minus 1 is the factorization of x squared minus 1, the difference of squares. This is a sum of squares. A sum of squares is not factorable. So if I just do what I always do, start with direct substitution, when I plug in 1, I don't get 0 over 0, I get 2 over 0. And 2 over 0 is not indeterminate. 2 over 0 is undefined, which means I do not have a hole, I have a vertical asymptote, therefore the limit does not exist. Always start with direct substitution. If you get 0 over 0, great, it's indeterminate. Use your algebra technique to simplify it. But if you do not get 0 over 0, then you don't need to do anything extra. You're done. Whatever answer you just got, that is your final answer.